All right, we'll go ahead and get started. Welcome back. I think today's actually a bigger day than yesterday, so it went so well that everybody were sad that they missed out yesterday and decided to come back and hear about ggplot. So any questions before we get started? From day one or day two? Anything about dplyr? Verbs are easy, right? Just function, changes the object in a really special way. Okay. Well, if there's no questions, then today is all things data visualization. We're using a key package called ggplot, and Allie will walk us through it. Allie, it's yours.
Okay, so as Matt said, today we're going to visualize data with ggplot, and whether you know it or not, everyone in this room has actually already used ggplot, but now I'm going to tell you what you actually did with it. So first, let's just simply talk about what ggplot can do and why this plotting tool is so powerful. You can make plots like this that you might see, or even these infographics you see almost every day in the news. And these infographics are actually by the BBC, and the BBC uses R specifically to make these graphs. And the reason they do that is because they say that ggplot gives you so much more control over how you're plotting things and works beyond a limited number of graphics. It saves time and effort because you can copy and paste things. You can just change the name of something or change a variable. And it updates, they can work with data that needs updating regularly with high reproducibility. And that's often what we are looking for as scientists. This simple quote here, or this quote here by John Tukey, it's gone. I'll read you the quote. It says, "The simple graph has brought more information to the data analyst's mind than any other device." And that's because as humans, we're very visual creatures. And so looking at a table to process information. But when we plot it, we can see patterns and ask questions about what we see. We can see easily from there. So, hey.
Okay. Just try not to bonk the keyboard. So
Yeah. I will try to touch the keyboard very gently. Okay, so with ggplot, the first thing we're going to talk about is mappings. So in the files that you have, there is a document called under the day 3 file, which is 3_ggplot, I believe, and it's the ggplot lecture. If you open it up and load the libraries at the beginning, you'll see that we're going to be using 2 data sets for today's talk, and one of them is chromosome. And you'll notice in the instructions in your document, I tell you to take a look or take a glimpse at chromosome, but I've only written chromosome in the console. So by now, we should all know that if we use the glimpse function or the head function or whatever, we can get this output here. And so looking at our chromosome data set, which is one you've already worked with so far, we can look now at these variables that we have and think about what we might want to plot. So this is just a quick question. It's not a trick question, I promise. So without running any code, what relationship would you expect to see between the length of a chromosome and the number of protein coding genes on that chromosome?
Positive correlation.
Yeah, okay. So Paul said positive correlation, meaning the longer the chromosome, the more protein coding genes, right? And so we can test this by plotting it. And so in that document I told you, which might actually have a different name than this here, but it will say ggplot2 lecture, you should have a chunk of code or an empty space in your console where you can type in this code. And go ahead and type it out by hand this time. It's a very short piece compared to what we'll be working with later. Pay attention to capitalization and everything. And just go ahead and run it and see whether or not Paul's hypothesis is correct.
Should we run it in Markdown or in
in the code chunk. If you put it outside of the code chunk, it won't run. So if you haven't loaded your libraries in that very first chunk of code, it won't work. So this is a good spot to use that run all chunks before button if you need to. So are people still plotting? Yes. So, while you're working, I was asked about spaces yesterday. You'll notice spaces in this code. I don't always put spaces in my code. Matt says that I don't allow my code to breathe enough. But it works with or without the spaces. Okay. Raise your hand if you have a plot. Okay, so most of you have a plot, so I'm going to go ahead and move forward. So your output should have looked something like this, right? So what we've done here is create a simple point plot. This is very much like what you did in the first class, where we've looked at the length of the chromosome on the x-axis and the protein coding gene number on the y-axis. And what we see is that there's mostly a linear relationship. So Paul said the longer the chromosome, the more protein coding genes. It looks like that's mostly true. But as I said before, what's interesting here is you can see there's a small chromosome or two that actually have quite a few protein coding genes. But we'll get into this a little bit more later. So what exactly did we do with this chunk of code? Let's go through that. So this is a very simple chunk of code where we've taken data and mapped it to a geom. So you see this little chalkboard definition up here. It's a statistical graphic, or in this case, just a graph, is a mapping of data variables to an aesthetic attributes of a geometric object. And so you see these different colored words match up here to our code. So our data is what we are mapping. These variables down here are the variables from that data we're mapping to an aesthetic. And in this case, our geometric object is a dot plot. So let's break this up a little bit more. And I should have mentioned, if you have any experience with ggplot, this will be the most basic introduction. So bear with me. The first line of data initializes ggplot. It tells it you want to make a plot, and you're going to tell it your data. At this point, it knows that you want to plot something from the chromosome data set, but it doesn't know what. So can anybody guess what happens if you run just the first line of code by itself? Yeah. So you get a blank square. Or a blank plot, because at this point it doesn't know what you want to do. So that's why we add a layer. So this, you'll see we have a plus, and this is kind of ggplot's version of a pipe, but I think we had some arguments over whether or not we should call it a pipe. But this is ggplot's version of add this, okay? So we have ggplot, and then we're going to put a layer called a gm point over top of it. This geometric function tells ggplot how you want to plot your data. So in this case, it's a dot plot, which is a geom point. And we've mapped the x and y variables to the aesthetic. So just a stylistic tip is you can put a plus sign at the beginning of a line, but generally you will always put the plus sign at the end of a line, never the start. So here you can see if we look once again at each little piece, we have ggplot, the data equals the name of our data set, so that's chromosome. We add our plus sign before the next line, go to the next line, specify our layer, map our aesthetics, and in this case our aesthetics are an x and a y variable. So this is your basic template of what you will start with every time. So you can change the data, the geometric function, and the mappings. But I want to make a note about this because this isn't necessarily how you're going to see these written every time, and that's because you can actually run this code without writing data equals or mapping equals. You can just write ggplot parentheses the name of your data set and then your geometric function and your aesthetics, because it knows that aesthetics are mappings. And this is generally how you will see ggplot code written everywhere, and mostly for the rest of this talk as well. So let's talk about geoms, that first layer that tells ggplot how you want to plot your data. So in this image here, how are these two plots similar? Once again, these are not trick questions. I've even put the code down here for you. Okay, so I heard some whispers, and I heard the correct whispers. They are similar in that they have the same x variable and y variable. There's one more way they're the same, and that comes from them having the same x and y variable, is they have the same data, right? They're using the same data set. So then the question is, how are these plots different? So you'll note I've highlighted the answer for you on the slide, so don't be afraid to say it. Okay, so these plots are different because they use different geometric layers, right? So one uses a geom point, in which we've made a dot plot, and one uses a geom smooth. And in this case, that creates a trend line. So it's the same data, it's just different ways to visualize that data. So our geoms are this geometric function, but how do you know which geom to use, right? This is usually the question. How do you want to plot your data? So there are lots of resources available to you. So if you're on our Studio Cloud, you can look to the left of your screen on the sidebar. There's a link to cheat sheets. You can go to the ggplot cheat sheet. You can also just Google this. It will show up. And you'll see that it gives you a list of geoms, and it even tells you 1 variable geoms, 2 variable geoms, if you have a discrete versus a continuous variable, these things. There's another resource you can use as well, the Data to Viz website, and this is a really kind of fun website to use because you can choose what kind of data you have in the top, numeric, categoric, and categoric, so on and so forth. And then you can follow this little chart and find out what sort of geoms you could use for your data. And it's really great because it gives you examples and I believe even some coding tips as well. So this was very useful to me recently when I wanted to make lollipop plots. So now in your code along, you will see a chunk where I just want you to figure out how to replace this scatter plot with a box plot, okay? And what you're going to be doing here is changing the geom. So take your best guess. If you can't figure it out, Google it. For the most part, these geoms have fairly intuitive names. So go ahead and give that a try. I should note at this point we're using the mitocarda dataset in case you are curious.
And that's something that so for example, chromosomes manipulated so it's mutually exclusive. If you're going to pipe something into it, if you're not going to pipe anything into it, you have to specify that. So by now it's and as Ali said, saying equals is nice when someone reading your code reminds them that that's a data set. But since it accepts only one argument,
Yeah, keep going.
This is where I went.
Yeah,
Keep going.
Yeah, we're in geoms, so
Here, this time.
well, it's already loaded, but yeah, that's just taking about it. So this is. Yeah. Yeah. Oh. I think I forgot to change that. How did I change that? Okay, so I think everyone has it. So how did you change this plot to a box plot? Yeah, so you just changed the name of the geom from geom point to geom box plot. Pretty straightforward, right? So this is our solution, and you get a nice box plot. So I just want to point out one more thing, is if you see a geom and you don't know what it does, you can type in the helper code for this, the same way you would a deployer function where you put question mark filter. So you can say question mark geom histogram, and it will take you to a little help page and your bottom corner. Another thing I find extremely useful, especially for plotting, is this ggplot2 tidyverse website. And if you go to this website, you'll notice at the top corner here, you see this little where it says reference. If you go to that, you get this page, and you'll see a list of all of the ggplot functions and all of the ggplot geoms. If you click on them, it describes them to you, how to use them, what information you need, and it gives you examples just like the help page, but what I find more useful is that it gives you the output of those examples. So you can see the graph and what exactly they do to it. Okay, so what do you think this chunk of code will do? So we know what one geom does. What do you think this chunk does?
Box plot with points jittered so they're not overlaid.
Yeah, so correct, but also there's one more thing about it. So you'll have a box plot, and you will have a geom point. Geom jitter is one of those less intuitive geoms, but geom jitter is a geom point where it jitters the points so that they're not completely overlapping. But here what we're doing is we're first adding a geom jitter layer, but then we're adding a box plot on top of that. So that individually, the geom box plot looks like this. You just made it. The geom jitter looks like this. But when we plot them together, it puts them both in the same plot. They are a layer, right? And this is actually one important note here is that order matters. If you put the geom box plot first and then the geom jitter, you will not see your box plots because they will be hidden under lots and lots of points. Okay, so now we know about geometric objects. Let's talk about aesthetics. So another quote from John Tukey, the greatest value of a picture is what it forces us to notice what we never expected to see, right? So this is going back to what I said before. You can look at a plot and really easily pick out little bits of information. But often we're plotting lots and lots of information on one plot, so we want to point out a subset of that data in some way. This is where we get into using aesthetics. So this is the plot we just looked at. This is the incorrect chunk of code on the bottom, you'll notice. But I want to ask, I've looked at this data set. I know that there's a score for rickettsia homologs. So I want to know on any of these chromosomes, are there more rickettsia homologs on any particular chromosome versus another? Okay? So we're going to look at using aesthetics to help us answer that question. So some of the aesthetics we can change include shape, size, and color. So here you can see we can plot points as circles, big circles, little circles. We can change them to triangles or squares or plus signs, and we can change the color of them. So here's a list of all the aesthetic properties you can change, including color, size, shape, fill, and alpha. And a really important note, if you want to change the color of your points or your boxes or your bars or whatever, and you change color and you don't see anything happen, it's because you need to change fill and vice versa. So if you change one and you don't see the output you expect to see, try the other one. Because on some of these geoms, the outline is actually the color and the fill is the color inside of the object. So for the next exercise, what I want you to do is you should have a chunk of code for a plot. I want you to change aesthetic values. Add color, change the sizes, play with your aesthetics, and just see what happens. What happens when you change the aesthetics for a discrete versus a continuous variable, those sorts of questions. So I'll give you a few minutes to play around with aesthetics.
Put the previous slide back up, or is that?
Yeah. No, it's not cheating. Almost always the most visually satisfying thing to do the first time is change the color. Because it's a very obvious output. We're going to go over that, but you can play with it and see if you can figure it out. So, yeah. Okay, so in this case, no. It's filled usually a variable, or you can put the zero.
So there, like, it's one of you. So it could be both. Or right, that's right. So in this case, it's giving you this thing. So you can't say anything because you can either do COL or
Yeah, so you can change it to a specific number. So like, for example,
or in this case, like
usually need a zero. Yes.
So if you did plus scale underscore there it is. That's a plus. So at this point,
That was
we added
before.
scale.
Maybe I just need
Yeah. We just get that.
Yeah, we're gonna do that. Okay, so has anybody not successfully changed an aesthetic of their graph? Excellent.
I have a question related to this.
Yes.
Back to all of those. So I understand the value of assigning a color or size difference based upon another variable.
Yes.
But what if you just wanted it all to be the same size or all the same color?
Excellent. I was actually just explaining that to someone else. Size and color can also have different inputs. So size can be a number. So for example, if you change it to 0.5, it makes sure that's smaller than the default. You can change a color to just, like for example, just blue. You can look up a list of colors that are accepts, but it often also accepts simple things such as I want the color red or I want color purple, but those need to be in quotations.
Okay. In single quotes or double quotes?
Like the double quotes, yeah. Okay, so some of you may have noticed that these aesthetics function differently for discrete versus continuous variables. So color, for example, if you have a discrete variable, R will assign each discrete variable its own color, right? But if you have a continuous variable, it will create a scale, in this case, from dark to light blue. It does the same for size, but you cannot map shape to a continuous variable, right? There is one more aesthetic you can map to both discrete and continuous variables. But first, here's just a quick example. Earlier, I asked the question, in this data set, do any of these chromosomes have more rickettsia homologs than another? And so in this case, I colored by rickettsia homolog score. And what we see is that the mitochondrial chromosome actually has a lot of orthologs. So that's interesting information. But there's another aesthetic that's a little less intuitive, and that's alpha. So go ahead and change alpha in your chunk of code and see what happens.
Are you going to talk about whether the variable is inside the aesthetic or outside the aesthetic?
That's next. Yeah. I'm going to show them in this.
Did you jump to 4, Alex, units, size 4 now?
Yes. So you should have this chunk of code written without the alpha aesthetic. And so what you'll add is that information. Okay, so how many of you are confused about what alpha changed on your graph? I have one. I have two. Lots of people. Cool. So that's because it may not be immediately obvious. Alpha, so does anybody think they figured out what alpha changed on their graph? Anyone? What do you think it changed?
Transparency.
Yes. So alpha changes the transparency of your points in this case, and that can be useful because often if you have a lot of data plotted in one place, the transparency of points allows you to see through those points and see points underneath of it. So, quick question. When I run this chunk of code, why do I get an error? No. So, one suggestion was that maybe the fill changes the transparency. Anybody else? Okay. So, this is an aesthetic, correct? We're changing an aesthetic. In this chunk of code, we have the aesthetic function and its parentheses. So what's wrong with this chunk of code? Yeah. So our fill needs to be set inside of that aesthetic function, right? So we can change it. So in this case, I've added back alpha, but you see now it's inside of the parentheses that are the aesthetic function. Now, side note, you can set some things outside of that, but it would be something like he mentioned before where you say size is 1, right? You can't map a variable outside of the aesthetic function. So before we move on, let's talk briefly about color and how color is a very powerful tool when you're plotting, but it can also be where many plots go very, very wrong. How many of you have looked at a plot and thought, wow, that is really hard to read, or wow, those colors are very aggressive? This is where I want you to note a couple of things. 1, less is often more. If you can keep a lot of your points black, for example, and point out something with 1 color instead of having 15 colors. Also, I want you to remember colorblind pairs. So in this case, on this little image here, I have the top bar is the colors, in this case, that I've chosen. But the 3 below it are what those colors look like to people with different types of color blindness. So what you see is that often these colors are very close to each other and indistinguishable almost. So it's good to be thoughtful about the color pairings you're choosing. We all know red-green color blindness is very common, or, well, not really common, but it's probably the more well-known type of color blindness. And so we try to steer away from using red and green together. There is a package you can download called Viridis or Viridis Lite. And this has colorblind-friendly palettes already built into it. And these are really good if you want to map continuous variables. So, for example, heat maps or other different things like that. And then one more thing is if you have a few colors, try to keep them very distinct from one another. So if you've plotted red, your second color probably shouldn't be orange, right? Because those are going to be hard to tell So in this case, maybe blue would be a better option. So that's just a note stylistically and for your reader. So let's move on to global versus local. So there are two places, well, there are multiple places in your code for plotting that you can map variables. You can map them globally or locally. So if you map them globally, what that means is that you're telling ggplot what you want in that very first line of code. So in the when you initialize your plot with the ggplot function, you're going to map that data there. And what that does is it says, okay, for everything in this plot, x is this and y is this, unless otherwise stated. Okay? So in this case, our geom jitter and our geom box plot will just default back to those aesthetics. So this is the same plot you made before, but you see our code is now much more simplified. So we've mapped x and y in the first line of code. We can also map aesthetics locally. So this shows you how mapping color in only the geom box plot will only change the color of the geom box plot layer, not the geom jitter layer. Another useful way to point out parts of data without coloring, for example, all of your points. So those are aesthetics, but you can also map data to different locally or globally. So in this case, in your Markdown, I've run a little chunk of code where I've created an object called large protein. And what I've done is run one of our dplyr verbs and filtered the protein size or protein length and created this large data set that has, I believe, around 10 proteins in it. And I've mapped this data using the geom label geom, and geom label creates labels. And I've told it that I want the label to equal the symbol. So that's another one of our variables. So you can see now what we've added to this plot is a subset of our data now has labels in it, telling us which proteins those are.
Why do you only label those?
Because I created that object, that data, to have only protein length over a certain size. So I have that chunk of code in there. You can see what I did. I filtered it. And then I mapped only that data. So that's why we only have symbols for those proteins, because they're the only ones in that data set. Okay, so we have this plot, and we have our data mapped. We have two geoms. Maybe we're really pleased with how it's looking, but now we want to clean it up. Okay, now we need to start thinking about labels and things like that. So here you'll see that when R plots your data, the default axis name for the x and y axis is the name of that variable. So in this case, that's not particularly pleasing or readable all of the time, so we want to change it. So we can do this by simply adding a line to our plot called labs, and this stands for labels. And this is a pretty simple function to use. In this case, I'm going to change the name of our x-axis to chromosome. So I just put in plus labs, and in the parentheses I wrote x equals chromosome. Why is chromosome in quotations?
It's not the data set chromosome.
No, so Paul says it's not the data set chromosome. You're right. But to carry that a little bit further, it's because it's a character string. So we're writing words, right? So we're telling it to put this character string in our x-axis label. So we have this plot with these beautiful colors on it. We've changed our X label. But this is a case where a legend isn't necessarily useful, right? So all of these chromosomes have a different color. That's fairly obvious just looking at it. So we don't necessarily need this legend on the side that tells us that 1 is red and 2 is a reddish orange and so on and so forth, right? So we can remove that legend by adding the guides function, and we just write fill. So this means the legend for the fill equals none. And that just removes the legend altogether from our graph. And I put this on here to demonstrate to you that almost everything you see on this plot can be changed to your visual preference, your aesthetic liking, whatever it is. If there is something on your plot you don't like, you can likely change it. You might, yes. You're right. Sorry. On this it says fill equals none. It should be color equals none. Sorry about that. Whatever the legend is for, so whatever aesthetic you mapped, that's what you would say. So if your size was an aesthetic that you had a legend for and you don't want it, you would say size equals none. So in your next exercise, you have this plot here. I want you to change the X and Y axis labels and add a title to your graph. If you don't know how to add a title, try looking for those cheat sheets or Googling it, or maybe just try something that seems intuitive, because it probably will work. Seeing what happens and then adding another thing. I do this all the time.
Why does the none have to be in quotes?
What's that?
Why does the none have to be in quotes?
I don't know why it has to be quotes. It's just how that particular function works. There's a lot of ways to get rid of your legend. This is what I find to be the easiest to remember. So if you end up Googling down the road, like, how do I get rid of my legend for this? You might find 5 different answers, all of which work. But for the guides function, it wants quotes for none. How's it going? Do we have X and Y labels? Some of you confident? So I'm going to go ahead and move forward. So does someone want to volunteer how they solved this problem? How they added labels to their graph? No? Yeah, so you use labs. How did you change the title?
Command is title equals.
Yes, you write title equals, and then you write the name of your title in quotations. So here you can see I have that plot as well. I changed the x-axis label to chromosome, y is protein length log, and title is the lengths of proteins encoded by each chromosome. And if you're eagle-eyed, you'll see that I have a typo. So now we have, yep.
So, if you have a short title, which just like goes on one side, is there a way just like to correct it, just to bring in the middle?
You have a short title that goes to one side.
Yeah, so it starts like very left, like just the beginning.
It
Doesn't look pretty.
Can you center it?
Yeah, I believe you can. I don't know the function off the top of my head.
I think it would be within the theme.
Yeah, it's probably within the theme. We're going to go over some of the theme options in a few minutes. So we have graphs. You now have the capability to make graphs out of your data set. But let's talk about some of the different things ggplot can do from there. So we're going to start with facets. And facets are a way to subplot or display subsets of your data next to each other. So in this case, I have my mitochondria data where I've plotted the chromosome versus the protein length, but what I've faceted on is the mitodomain score. So this divides it up into mitodomain, non-mitodomain, shared domain, and NA. And we see all the same information for each of those all the way across. And so you'll see here, I wrote facet grid cols equals var's mitodomain score. So columns mean I wanted the columns to be this variable. So for exercise 6, what I want you to do is play around with facet grid versus facet wrap. So in this case, you're going to be plotting that same information, but you're going to be faceting it in different ways. And one note here. You'll notice on this slide and in your data or in your markdown that I have assigned this plot to an object. And this is just to let you know, you can assign these to objects and then take that object and add different layers to it. So in this case, we're going to take our object Q, which is our ggplot, our geom point of the mitochondria data, and add the layer facet grid or facet wrap. So go ahead and try these different chunks of code and see what happens. And I will talk about what the period and the tilde mean as you go along. So go ahead and try running them. See what sorts of options you get. Okay, so these are your outputs. So you'll see that your first function, facet grid, period, tilde HG19 chromosome, gives you these columns. If you do facet grid but change the HG19 chromosome to the first position and the period to the end position, you get rows. And if you do facet wrap, just tilde HG19 chromosome, you get a grid style. Okay, so let's see if I can explain this clearly. The period tilde HG19 chromosome. The tilde means by, okay? So rows by columns. So in this case, our facet grid, our first one, we have a period by, the columns are HG19 chromosome. The period means we're not making rows any particular variable. So that means, I don't know if any is the right way to put this, but we're not mapping anything in particular, but we want our columns to be HG19 chromosome. And when we change it to HG19 chromosome tilde period, it means we want rows that are the chromosome data by nothing in particular. For facet wrap, you'll see I left out the period. It does the same thing. So you can do it with or without. So what happens if we facet HG19 chromosome by a different variable? So this might be a little bit easier to explain to you what the period does. So here I have faceted the rickettsia homolog score by the HG19 chromosome variable. And if you look, this is rows by columns, right? So our rows are homolog, non-homolog, and ortholog, going across in rows, right? But our columns are mitodomain, non-mitodomain, shared domain, and NA, right? So this is giving us little subsets of data. So that very top left-hand corner is all the things that have rickettsia homologs and a mitodomain. And all the things in the bottom corner, in the bottom right, are rickettsia orthologs that don't have a mitodomain score. Does this make sense? This is like a confusing concept for me to explain. So please let me know if you have any questions. I will assume silence means you don't have any questions, so if you have any, now is the time.
I'll just interject one other point here. The ability to facet your data and divide it to look at relationships between different variables is one of the more powerful functions or features of ggplot, and is one of the reasons that people use ggplot for exploratory data analyses. So being able to ask questions about certain relationships between variables, instead of making 12 different plots individually, you add one line of code and it splits your plot up into 12 different sub mini plots. Mm-hmm. So, asking questions about something not very intuitive, like a rickettsia homolog score compared to its location on the chromosome, might not be such a intuitive thing. But what you'll find is when you are thinking about your data, you can ask questions about relationships between different features of your data. Let's say a subcellular localization, or you could ask it about an age of a mouse, or you could ask, basically divide it into a different categorical variable and then plot and say, okay, well, if I subset my data into a certain categorical variable, what does it look like? So facet is the name of the function in this case that allows you to split your plots to look at all of the relationships at once by certain categorical variables or features of your data.
Okay, so I think that's probably the most complicated thing we covered today. So let's look at some other things we can do with our plot. This is one I wish I could do to people's plots while I'm reading them, and this is coordinate flipping, okay? So I have a plot here. It's actually the same plots you've been looking at before, but this is before I changed the names of the chromosomes and factored them. So here you see I have on the x-axis, all of my tick marks are just gobbledygook, right? Who can read that? Okay, no one. So this is where coordinate flipping can be very useful. So we can add a very simple little bit of code to our graph, and it's just plus, and the function is chord flip. So COORD underscore flip, parentheses. And what that does is we've set an x and y variable, but it's just plotting it with our coordinates flipped, right? So our x and y are now flipped. So this is extremely powerful because now you can read what my x variables are, right? Now you can see that it's chromosome 20, not just a blurred line of text. This is really useful when you're plotting information for individual genes. We often see these graphs that have gene names that are crooked and like at an angle underneath of our graph because we want to fit it in, but you can't read it if it's all straight, right? We can coordinate flip and make it easy to read because that way we can just read it without moving it and make it quick and easy.
You could also flip the numbers, right? Like the chromosome numbers. They were written as you read them.
You
horizontally.
can.
Flip them to be vertical.
You can. It's just not very easy to read it that way, right? It's not like I'm going to be standing like this. This is just like a really nice, clear way for the text. I mean, reading a number across the bottom is not difficult. So,
For the chord flip, I noticed there's nothing in the parentheses. Does R just automatically apply to everything?
it just does the one thing where it flips the x and the y. I think there are different things you can change in it, but usually all you need to do is add the coordinate flipping. If you want to know what you can change in it, look it up. It's in the on the reference page. Okay, so and next, this will probably get to some of the questions you have about individual aspects of your graph. For example, our question about the title alignment. Let's talk about themes. So, we can change different aspects or visual aspects of our graph by changing different parts of our themes. And what I'm going to show you first is going through and changing different parts one at a time. So in this case, I have this plot. We're back to my regular chromosome numbers. And I have a title, but I want my title to be bolded. So I'm going to add the function theme. I'm going to tell it I want to change the plot title. So I added plot title. And I put equals element text. And inside of that, I tell it I want it to be bold, and I want to change the size of the text. Now, I realize that this is like a lot of things all at once. That you're like, how will I remember that I need to write element text face equals? I have to Google it. There are lots of different ways to change it. It might come to you, but I find I still have to Google it. So if I do that, you see that now we've changed the size of our text for the title, and it's now bold. So that's one thing. Then we can change the legend background. In this case, I have my little legend over here telling you the colors for each rickettsia homolog score. And I'm going to tell it that I want that rectangle to be gray, but I want the outline to be black. So this is another good place to show you the difference between fill and color. So the fill is gray, the color is black. So if I run that code, I get this, right? So now you can see my legend box. It has a gray box that it's in with a black outline. If I want to move that box, so right now it's over here on the side, but maybe I want to put it underneath of my plot to save some space horizontally. So I can move my legend position. So I just add legend position equals, and this one's a little bit more intuitive. At this point, I just put bottom. So now my legend is down here underneath of my graph. So you could put top, you can put right, left, whatever. There are lots of options. You can even overlay your legend onto part of your graph. Let's say you have an empty space, an empty corner, you can put it there. But But if you don't want to go through and change every single aspect of your plot individually, one at a time, there are preset themes. So here is the default theme ggplot gives you. I can change it to theme black and white. This gives my plot a nice black outline with a white background. And there are a number of these already preset or available in ggplot, like black and white. I think there's a dark one, minimalist. There's these different built-in ones you can look up. There's also ones you can download. So I showed you the BBC plots earlier. So the BBC and The Economist and things like that, they've created their own themes. And if you like those themes, you can just add like the Economist theme to your plot and you get all the colors The Economist uses. Or you can download the ggplot package and get all the colors that the BBC uses. So finally, you have a graph, you're happy with it, you want to keep it, you want to show it to the world. So let's save it. There is the simple user interface way to save it, where you go to your graph, you right-click on it, and you click Save Image As. I have done this plenty of times. I usually do it when I want to quickly show somebody a graph. But I find that I more often than not want to do it in code using the ggsave function. So this doesn't have to be part of your ggplot code. It's a separate line of code. So let's say you make your plot, you like it. A few lines down from that, you can put in this ggsave function. And you're just it's gonna save by default the last plot on your screen. And you can see I can save my plot as a PDF or a PNG or a JPEG, whatever it is you like. And you simply write in quotations, the simplest way to do this is ggsave, and then in the parentheses, in quotation marks, you write the name that you want your plot to be. But there's what I find the most useful about this is you can actually specify different aspects of your plot dimensions. So for my PDF, I can say I want a 6-inch by 6-inch plot. So this gives me exactly the size I want.
Are pixels an option too?
I think you can. I think you can change the DPI. I'm fairly certain you can. So, where will it save it? Does anybody know where it will save?
Files.
In your files. Okay. That's accurate, but it's going to be more specifically alongside your RMD. So, this is what we talked about yesterday. When you have your working directory, and you see where you are working, that's where it will save it. And Akshay mentioned yesterday the power of projects, where everything's in the same place. I highly suggest using that. But if you want to know where your working directory is, I sent out a Slack message. If you're not on Slack, the very last line of your lecture code along has the words getwd, but there's an underscore in it. It won't work. So please take the underscore out, because I always forget that it doesn't have an underscore. But if you get WD, it tells you exactly the directory that you're saving your plot in.
Allie?
Yes?
This is on the cloud.
Yes, this is on the cloud. If it's on your computer, you can set it to a space on your computer.
Like, I know DMPI, they like all the work that we are doing to save the file server.
Yes.
Can you specify the file server as a working directory?
Yeah, so Paul is asking about whether or not we can set specific file servers or whatever as our working directory. This is, once again, where I use projects. When I start using R, I create a project. And when you create a project, you get to specify where that project lives in your computer. So I will go to my DMPI working directory, put my project wherever I want it to be, and then whenever you open that project, it automatically changes your working directory to that location. So that's really useful, because sometimes you might change your working directory for a different project, right? And then you go back and you're saving things in the wrong place. So if you want any help on like using projects, I don't know if we're going to talk about that on Friday or not, but we're always happy to answer any questions outside of class. So with
I got a question about the saving. So
Yes.
you said it will save the last plot. What if you have a window where you had two plots that you generate? You know, side by side, you can click on. Is it only going to save the active one, or?
Yeah, that's a good question. So Tim is asking if you have in your console, in like your code chunk, you've plotted two different plots, and then you put your save function. Which plot is it going to save, or will it save both of them? The answer is that if you run your first plot, and then your second plot, and then the GG save, it will save the second one. You can either divide your plots up into different chunks, or put another GG save right before it. A lot of times, people don't necessarily put that GG save code in with the code chunk that generated the plot. They put it in its own separate chunk after, because that way you're not resaving the plot every time you run the plot in R. You can also just hashtag it out. It's kind of user preference. So with that, you should be able to plot all sorts of things now. And if you forget the basic structure of your ggplot, you can just look at the ggplot2 template or the cheat sheet. They have this beautiful little template that shows you this is your ggplot. These are the things that are required, and some things that aren't required but have sensible defaults, things like that. So in your files there, you'll have two different homework documents. This title may not be completely correct, but you'll have ggplot2 homework and ggplot2 mitocarda homework 2. The first one is very simple. You're going to be working with the chromosome data. The second one is with the mitocarda data. And what I encourage you to do is there's a point where I ask you to generate a plot once by just like typing out the whole code for the ggplot. It's not a particularly long plot, I believe. But then you can also go back and just copy and paste code from this lecture RMD to create plots and change variables. Both are good. Matt has told you before, we give you this so you can copy and paste. I found for ggplot, at least once or twice, typing out a plot by hand has kind of helped me remember what things I have to have. But yeah, so go for it, and we're around to help. If you have any questions today or tomorrow, we'll be here to answer them.
Any more general questions before we finish up? Okay. Thank you all, and we will see you tomorrow for reader and stringer, importing files and a little bit about working with strings. Okay, thank you.